morning. We begin lecture 39. There was a request from the students to do it as a review lecture just like we did last time. So this is a review of lectures 19 to 36. Just to avoid confusion, the portions is lectures 1 to 36. It's just that we are the review part, since we have already covered lectures 1 to 18 in the previous review, we are focusing on lectures 19 to 36. By way of instructions, these have been shared through Moodle just for clarification. A handwritten formula sheet, whatever you want to write, integral formulas, derivations, whatever it is permitted. Please bring your calculator. The question paper will be distributed at 7:50 like last time. As planned, we will have a doubt clearing session on assignment 4 today evening, 5 to 6 p.m. Okay. So let's quickly run through. Again, most of this is a material that is probably things that you will remember, but just sort of putting it all together in a single canvas is what we are trying to do. So I will just write down approximately what the, there is overlap of lectures, but what the points are in each of the lectures. The lecture 19 was around the time we were finishing up our discussion on Rayleigh fading. So the assumptions of Rayleigh fading. And there were a few assumptions in the basic model. I thought it's good for us to keep that in mind. Multipath. Large number of components that are propagating from the transmitter to receiver. There is no line of sight. There is no dominant path. That is also part of the model. And the multipath are arriving in all directions. I believe these are the essential assumptions that we have made, and based on which we have obtained the properties of Rayleigh fading. Okay. This led to a brief discussion of a simple example of a transmitter and a receiver in the presence of a reflecting wall. Again, that was an example from Say and Vishwanath. And with respect to this example, we observed some results. And the insights that we obtained was there is a notion of coherence distance. If you traverse beyond a certain distance, then the channel has a substantial amount of change. We call that as delta xc. We said that's proportional to lambda by 4. That is lambda by 4 for this example, but in general it's proportional to some fraction of lambda. That is what is the important thing that we take away. Once you have coherent distance, you also have coherence time, because coherence time is delta xc divided by v, the velocity with which you are moving. And this also, we went back and reinterpreted the result when there is a there's a second copy of the signal through the reflecting wall, that there is a notion of coherence bandwidth. And this we showed was proportional to 1 over the delay between the first and second paths, but in general it will be proportional to, inversely proportional to the delay spread. The presence of Doppler is a important element in our understanding of wireless channels. The Doppler frequency can be positive or negative. The maximum possible is proportional to V divided by lambda. This is also written as V, writing lambda in terms of the carrier frequency, V times Fc divided by c, which is the speed of light. Okay, so therefore any carrier frequency we can assume what is the maximum Doppler, and of course based on the angle between the direction of propagation and the direction of motion, then you get this Doppler times cosine of the angle. So the maximum Doppler spread, or what is the maximum range of frequencies that we can expect in a fading channel, turns out to be 2 times Vfc divided by c, or 2 times the maximum Doppler, because it can go all the way from minus Fd to plus Fd. Lecture 19 also took us into a discussion of coherent detection. Basically, now that you have a model for the channel, what are the aspects of coherent detection? Coherent detection, if your received signal R of t is equal to some z of t times s of t plus eta of t, coherent detection requires you to know Z of t. So we said that there are two aspects to coherent detection. One is channel estimation, and you must enable or assist the receiver to do channel estimation, and you do that by transmission of training sequences. So maybe this is aided by the presence of training sequences which are inserted at the transmitter. These are overhead, they do not carry information, but just that your coherent detector can do channel estimation. Now, apart from channel estimation, depending upon the changes that are happening in the channel between your channel estimates, you would also need to do channel tracking. And this channel tracking has to be based on the decisions that you have made using your demodulation scheme. So it is actually decision directed channel tracking. So you would use the decisions that you have already made and do the channel tracking. So it's actually called decision directed channel tracking. So channel estimation, channel tracking, both of these are needed so that we can build our coherent detection scheme. Now, if we do not want to do coherent detection, if we do not want to do coherent detection, we said that there is an alternative, that is the presence of differential detection, differential modulation and differential detection. So that was lecture 20, took us into the discussion from coherent on to differential. So in the context of differential, we have to encode the information using a differential technique. Differential phase modulation, that is phase modulation is what lends itself very easily to differential modulation. And differential phase modulation basically says that the phase that I transmit at time instant k is a phase at time instant k minus 1 plus delta theta k. And the information that I want to transmit at the time instant k is in delta theta k. This is what is decided by the information bits. The thetas themselves do not carry the information. The delta theta is what carries, decided by the information bits. Okay, now how many levels I have, what delta thetas I use, all of that is part of the choice of the modulation method in information bits. Okay. And the differential, the counterpart would be that we do not need to do coherent detection, but we can get by with differential detection. Differential detection, which is given by RK minus 1 conjugate, and we can show that this is equal to alpha squared, or it's the same as mod z squared times e power j delta theta k, plus there are 3 noise terms. Okay. So again, we wouldn't worry too much about the noise terms, because their presence is known, and so there is a penalty that we are paying when we do differential detection, but the good news is that you don't need to do channel tracking or channel estimation. We also discussed briefly the advantages and disadvantages of coherent versus non-coherent. So the understanding is that coherent detection will do better than differential detection, okay, in a fading channel. So if this is coherent, this would be differential. However, if you have channel tracking errors, then you will find that you will have a error floor due to channel tracking. And since you're not doing channel, this is an error floor due to errors in channel tracking, and the differential detection does not suffer that. So there are scenarios where you may prefer to do differential detection. So the advantages of differential detection from that figure we can capture in the form of a single statement. Basically, the fact that a coherent detector has an error floor. Coherent detector has an error floor at high Dopplers. And that's because of the requirement of channel tracking and the limitations of our ability to track fast fading. Okay, this is what makes differential detection attractive. However, we need to keep in mind that differential detection makes the assumption that it's a flat fading channel, because if it's frequency selective, then the differential detection becomes not a feasible option. So differential detection only for flat fading channels. Flat fading channels. Okay. So if you were to then map modulation and demodulation, so if I do coherent, that's a good option. If I do differential, good option. We've also looked at coherent and differential. Nothing prevents me from doing that. Really did not gain anything. And of course, if I do differential modulation and try to do coherent detection, also there was no advantage. In fact, there was some disadvantages with the cross combination. So basically, there is coherent techniques, there is the differential techniques, and each of them have their benefit for us in terms of our usage in a fading channel. Okay. By the way, I'm sort of running through, but if something needs a little bit of clarification or something needs to spend a little bit more time, just indicate. I'm assuming this is just a sort of a refresher, so that you get all the pieces together at one stroke. Okay, once we had our basic hands around coherent modulation and the differential coherent techniques and the differential techniques, we focused our attention in lecture 20 on the probability of error. Probability of error of BPSK, again, this is something that we used from digital communications. We did not derive this. Probability of error of dBPSK in AWGN channels will be half e power minus gamma. And given that you have these types of expressions for the probability of bit error rate, then we said that we can derive the probability of error of these modulation methods, for example, BPSK in fading, by using the fading distribution. So it would be 0 through infinity, the probability of error at a given SNR times the distribution of the SNR f gamma of gamma d gamma. Okay. And we also, using a change of variables, showed that once you start from Rayleigh distribution, you can then derive the SNR in a Rayleigh fading environment, which is f gamma of gamma is given by 1 over gamma e power minus gamma by gamma, where gamma is equal to expected value of gamma. Okay, that's the PDF, and using that we will plug into this expression and derive. So we also went through the exercise of deriving in lecture 20 the error rates in fading. So probability of error of dBPSK, that was a fairly straightforward integral for fading. Basically, it was a one-step answer, which came out to be 1 over 2 into 1 plus gamma. On the other hand, the probability of error of BPSK, because of the Q function, did require some additional steps, a change of variables, and then the use of standard results. The answer came out to be 1/2 of 1 minus square root of gamma divided by gamma plus 1. And in both cases, we were interested in the asymptotic approximations. So the asymptotic approximations in this case was 1 over 2 gamma. In this case, it was 1 over 1 by 4 gamma, indicating that BPSK had approximately a 3 dB advantage over differential BPSK in the context of a fading channel. Okay, lecture 21 was the focus, or what we highlighted in lecture 21 was a augmentation of our design or understanding of wireless channels. Again, we didn't spend too much time, but we did indicate that lecture 21 one of the key aspects of wireless channels is the role of error correction, forward error correction. Okay? And we also showed that interleaving is absolutely crucial for the success of forward error correction in a fading channel. We basically showed a square interleaver, how you would input the data, how would you read the data. So the summary of that discussion was that the fading channel, because of the correlatedness of its behavior. So once you go into a fade, what you are likely to encounter in coherent detection is consecutive symbol errors. Consecutive symbol errors. So which means this is nothing but a burst of errors. Most of our codes are designed so this would give you a burst error pattern. Most of our error correcting codes like convolutional codes work well when the errors are random, and the role of the interleaver turns out to be very critical because it makes the errors appear random. Errors appear random in terms of position, not in terms of the values themselves. Basically, the error has occurred, the position appear at random locations. And where does this occur random? To whom does it look random? To the decoder. Yeah. So basically, the receiver is there. After that, there's a de-interleaver, and then the decoder is there. The decoder is what is seeing. Oh, okay. I see errors which are not a burst errors, but they are. So basically, they are at random locations, as seen by the decoder. As seen by the decoder, and this was more to augment our understanding of why we always see interleavers in the context of fading channels. Okay. Having completed that brief sort of interlude, we went back to writing down a BER table. We wrote it down for I believe BPSK, QPSK, MSK, DBPSK, coherent FSK, and I think non-coherent FSK. Okay, so basically there was a table, and in each of those cases, what we have written down is the probability of error in an AWGN channel. Usually it's a form of an exponent or a Q function. From that, we derive probability of error in fading, and from there we wrote down the asymptotic behavior at high SNR. At high SNR. Again, it's useful for us to be able to go from the expression in AWGN to fading, and then an understanding of what the asymptotic performance is going to be. Okay. Somewhere along the line, we also indicated that sometimes it's difficult for us to evaluate the Q function if you don't have a computer. So therefore, there is an approximation or an upper bound which is helpful for us. 1 over root 2 pi e power minus z squared by 2 divided by z. And in the assignment number 4, you have seen that you can actually upper bound and lower bound it so that you can actually get a range of values. Now, in order for us to be able to do these computations for the different modulations, different fading environments, so we did spend some amount of time understanding the statistical characterization of the other types of fading. So relay fading has been the focus up until this point. So lecture 22, we did look at the following: the Rice or the Ricean fading. So it would not be nothing but a random variable with a Ricean PDF, FV of V, that's a PDF, V divided by sigma squared I naught of SV by sigma squared e power minus V squared plus S squared by 2 sigma squared. The sigma relates to the non-line of sight component, the other what we would call the Rayleigh component, and the S relates to the line of sight component. So S squared is equal to M1 squared plus M2 squared. Those are the means of the real and imaginary part, and using this expression, we said that we could characterize Ricean fading in terms of a Rice factor, which is given, usually use the notation K, which is defined as S squared by 2 sigma squared. So in other words, this would be proportional to the power in the line of sight component, so power or line of sight component divided by the power in the non-line of sight component. Okay, and we also showed that K equal to 0 means there is no line of sight component. That actually does give us the Rayleigh distribution, and K tending to a very large number, so something of the order of 10, 20 like that, then we say that the line of sight component starts to dominate, so the fluctuations tend to become less and less significant, so it starts to look more and more like an AWGN channel. So Ricean fading actually turns out to be a superset of Rayleigh fading. Rayleigh fading is as a special case. We also studied the Nakagami M fading because in terms of the analytical expressions, it's difficult for us to work with the Rayleigh distribution. So the Nakagami M is a useful way of describing fading, and here again the distribution Fv of V, I'll just write it down, you can look up in your notes, M minus 1 factorial M by gamma raised to the power M V power 2M minus 1 e power minus M V squared by gamma. Okay. And we have also showed, or at least stated in the class, that Ricean fading and Nakagami M fading actually cover the same range of fading distributions. In fact, the Nakagami M actually has a slightly broader range, and we can show that there is a relationship that maps the Nakagami M and the Ricean fading very closely. So the relationship is M is equal to K plus 1 squared divided by 2K plus 1. M is the Nakagami fading parameter. We also were interested to look at the distribution of the SNR, not necessarily the fading PDF. So in the case of Nakagami M, we showed that F gamma of gamma, this we derived in the class, M by gamma raised to the power M gamma power M minus 1 divided by M minus 1 factorial e power minus M gamma by gamma. Okay. So Rayleigh fading, Ricean fading, Nakagami M fading, all of them have different added and different ways of understanding and being able to work with the fading channel. We also indicated that using the moment generating function has got a lot of advantages. So again, lecture 22 still continuing. Moment generating function is given by phi x of s equal to minus infinity to infinity fx of x e power sx dx, and we said that we could interpret the moment generating function as an expected value of e of sx, or that we could also interpret phi x of minus s as the Laplace transform of fx of x. Okay, so regardless of which interpretation we take, the usefulness is when we try to develop it, and one of the things that is very useful for us is the DBPSK family. Now becomes very easy for us to evaluate, because probability of error of DBPSK in fading becomes just evaluation of the moment generating function. So let me just write the expression. It's 0 to infinity half e power minus gamma f gamma of gamma d gamma. That would be the for any distribution of the SNR, and so all we need to do is obtain the moment generating function of that particular fading distribution phi gamma of s, and replace it with s is equal to -1. That will give us the expression. Okay, just as we had coherent detection of BPSK as q of root 2 gamma, there's a whole range of family of modulation schemes for which you will get the expression as some constant times gamma. So for example, one of the most popular modulation schemes that we encounter in mobile communications is Gaussian MSK. So it's Gaussian filtered MSK, and the Gaussian filter has got a BT of 0.3. This is the modulation scheme that is used in GSM, and this one has got a error function which is q of square root of 1.4 gamma. So basically beta is equal to 1.4. Now since we have already computed it for for BPSK, we just by substituting showed that q of root beta gamma, if that's the BER in AWGN, then the probability of error in fading will be 1/2 of 1 minus square root of beta gamma by 2 plus beta gamma. Okay, and the asymptotic behavior will be 1 over 2 beta gamma. So actually the results that we have obtained are very useful in terms of a very broad class of functions. And using these observations, we did make the following, the probability or the BER of coherent BPSK in fading is less than BER of GMSK. That's very easy to show, because what is the SNR difference between the performance of GMSK, because both of them have got a Q function in Rayleigh fading, and we can show from the asymptotic expressions that this is better than BER of DBPSK. Okay. So use the asymptotic expressions to sort of see where these graphs will fall, and then you can show. And of course we did show in class that for a particular, to achieve a particular BER, the gamma of GMSK based on the expressions that we have is gamma of BPSK plus 1.55 dB. So it's approximately 1.55 dB poorer than in terms of performance. Okay. So let us move on to the lecture number 24. What happened to lecture 23? Okay, yeah, the table and other things came in lecture 23. Okay, lecture number 24. One of the applications of moment generating functions, which we saw first in lecture 24, but subsequently also saw it again when we did diversity. So lecture 24, an understanding of what the moment generating function is and what is the benefits of that. We said that if gamma diversity comes out to be gamma 1 plus all the way to gamma m, if we, at that time we did not have a scheme that achieved this, but if this was the scenario, then the moment generating function, and they are all independent independent variables, then the moment generating function of gamma diversity of S this would be a product of the moment generating functions I is equal to 1 through m psi of gamma I of s, and once you have the moment generating function, you can use it to compute the BER. You can also do a inverse Laplace transform to get the PDF also. Both of those methods are used, so that's one of the reasons why we work with the moment generating function. So after we finished this discussion, lecture 24 took us back to our understanding of the multipath fading channel. So the multipath fading channel. Multipath fading channel we had described earlier, want to recapture that in the following manner. The received signal R of t is a superposition of many copies of the signal. Each of them has got a complex gain term. The amplitude is alpha n, the phase is e power j phi n. This is a function of t and tau, and the received signal, if the complex baseband representation was u of t, then this would be u of t minus tau n of t. Okay. And this also led us to describe the channel in terms of two variables. One is the delay dimension, the other one being the time dimension, and this is a description of the channel using a two-dimensional model, n times alpha n of t e power j phi n t comma tau delta of t minus tau n of t. Keeping in mind that we cannot call this impulse response or treat it like an LTI system, but always keep in mind that our description is that it is a two-dimensional description of the channel, and what we are saying is at every time instant, if you take a snapshot, the channel is going to look like it's got some behavior in terms of the different delays. And because it's time varying, these gain coefficients and the delays can change as time progresses. So basically what you see is a series of snapshots in time, which is what is captured by h of t comma tau, and this is our basic understanding of the fading, multipath fading environment. So the focus of the next several lectures was to develop a comprehensive characterization of the fading channel. So the first one that we did was we took this expression for E of h comma tau and we computed the autocorrelation. E of h of t comma tau h conjugate of t plus delta t comma tau, and wrote down the expressions for that and showed if you denote this as the autocorrelation function, it turns out that it did not depend on t, it only depended on delta t, and the expression was some constant times the 0th order Bessel function of the first kind 2 pi fd times delta t. Okay, so let me just clarify, this is a constant, this is our Bessel function, 0th order Bessel function of the first kind. All of this are readily available in tools like MATLAB. We can program the, we can get the different values. So the shape of the Bessel function we showed or we sketched in the class looks like a sinc function, but focus on the fact that it starts off at a maximum at when the argument is 0 and then sort of monotonically drops when you start moving as delta t increases. So the focus of interest is primarily not till you reach the 0 crossing, but what's the behavior for small values of delta t. So that's where the region of focus is, and we found that depending upon the Doppler value, the slope of the autocorrelation function will change, and in fact as you keep decreasing the Doppler, the rate of change or the autocorrelation becomes higher and higher, and eventually for 0 Doppler the correlation remains constant. Basically it's at a maximum value, which means that the channel is not changing at all. So the steeper the Doppler or the autocorrelation function, the faster the channel is changing, or which also means that the Doppler is higher. We also did a Fourier transform of the Bessel function and showed that the behavior or the since this is the autocorrelation, that what you take when you take the Fourier transform, you get the power spectrum, you get a shape which is bounded between plus Fd and minus Fd. The expressions are given here. So let's just write down the so if I have autocorrelation function, P0 is a constant, J0 2 pi Fd times delta t. The Fourier transform comes out to be P0 divided by pi times Fd square root of 1 minus rho by Fd whole squared for mod rho less than Fd. Okay, and is equal to 0 outside. Okay, so that's expression. This is what it looks like, and we have now been able to relate the time variation which is caused by Doppler to a spectral characteristic, which says there is a variation of the spectral content from 0 frequency to plus minus Fd. We observed that the channel is a multiplicative channel, because when we do fading, it's a multiplicative factor. So basically in the time domain, it's a multiplicative operation. So which then says that in the frequency domain, it will result in convolution. So which means that whatever is the spectrum, you're going to convolve with a shape that has got spectral content between minus Fd and Fd, which results in spectral broadening. So the understanding of spectral broadening, which is caused by multipath fading, was introduced in this lecture. Spectral broadening, but we also showed that for most of the wideband signals, it's very insignificant. It does not matter much, because the spectrum, if this was the spectrum, what we are saying is the spectral broadening is going to be that there is some widening of the spectrum on this side and a little bit of a smear on the other side, and this range of is basically Fd. Right. So the additional shift or the smearing happens with proportional to the Doppler frequency. Okay. But then if spectral distortion is not the issue, then what is the issue? It turns out that it is the channel characterization in the time domain. So we said that what we need to take away is the coherence time, because the channel keeps changing, which says how often should I estimate the channel, and that is related to the channel coherence time, which is given by 9 by 16 pi Fd. Okay, this is for the autocorrelation function to reach a value of 1 by root 2. Okay, so that's how we have obtained this expression. Okay, we then computed in lecture 25. We computed the coherence time for different Dopplers. So basically coherence time is inversely related to the Doppler. So we also gave the rationale for the GSM system design. Why did we design the slot of a certain duration? Why did we put the training sequence in the middle? What happens? What can you tell about if one burst is affected by a fade? What happens to the next time instant that the same user is going to transmit, which will be 8 time slots later? So rationale for a GSM system design, a lot of it is tied to our understanding of coherence time, and therefore that is what we were able to do. GSM system design. Now, along with the temporal variation, we also saw that there were two other elements that are very useful in understanding the channel, and those are the characterizations of the time behavior of the channel, and one of them was the level crossing rate. Level crossing rate. So given a certain threshold for fading, how often does your fading envelope cross that? This is given by NV equal to root 2 pi times FD rho e power minus rho squared, where rho is given in terms of V threshold divided by V RMS. Okay. Now, very often when we talk about fading, we may not write down the thresholds in terms of the amplitude, but we may write it down in terms of a threshold power level with respect to the average power level. Okay. So, the threshold power level is proportional to VTH squared. This is proportional to V RMS squared. So, please make sure that it's if you are given in terms of the powers, you can still translate it into the correct value of rho. Basically, what you would have to do is rho in that case would become square root of the threshold power level by square root of P and of P bar, and you should be able to get the value of rho. Once you get the value of rho, you can translate it into the corresponding okay. Along with level crossing rate, we also wrote down an expression for the average duration of a fade. Now, this is also a useful indication of saying how many symbols are likely to be affected if my signal goes into a fade. Average duration of a fade denoted by ADF. This is T fade with a bar average. This is given by e power rho squared minus 1 divided by root 2 pi FD times rho. Again, rho is computed exactly in the same manner as in the previous case. Having fully understood the time variation, we went on to characterize our understanding in terms of describing the fading channel in terms of the wide sense stationary uncorrelated scattering model. Wide sense stationary in terms of the time variation, uncorrelated scattering in terms of the time dispersion. So, this was characterized by this expression, expected value of h of t comma tau 1, h conjugate of t plus delta t comma tau 2. Notice tau 1 and tau 2 correspond to different multipath components coming from different interacting objects. We argued that they are uncorrelated with each other. So, therefore, this autocorrelation becomes RH of delta t. It depends only on delta t, and it is uncorrelated across the different delays. Delta of tau 1 minus tau 2. So, basically it is only correlated for a particular delay. So, this part was the WSS portion. This is the uncorrelated scattering portion. So, then we said, okay, having fully understood the time variation, which is the wide sense stationary part. Now, what about understanding the scattering part or the delay dimension? So, for that we computed RH of tau. Basically, we have set delta t equal to 0 in the previous expression. This comes out to be expected value of mod h of t comma tau whole squared, and this is what we refer to as the power delay profile. Power delay profile. This is usually obtained through channel sounding, but again assume that the RH of tau as a function of tau just says where are the multipath components, where are the strong ones, and then eventually the multipath components die down below a certain threshold, and we now are able to characterize this is the multipath behavior of the channel. Now, the characterization of this in terms of the average delay for a continuous power delay profile, it would be 0 through infinity tau times RH of tau d tau normalized by the total power delay area under the power delay profile graph RH of tau d tau. This is a constant, let us call that as some P naught, and basically you can compute tau squared average and then sigma tau as square root of tau squared average minus tau average whole square. And this is the RMS delay spread, and this is a very important parameter that characterizes the time dispersiveness of the channel, RMS delay spread. This is what also tells us whether we need an equalizer or not, and therefore this characterization of the power delay profile is very important for us. Okay. Most often we do not have a continuous power delay profile, but we have a discrete power delay profile. So in that case, the computation will become a summation rather than a integral, basically tau n RH of tau n divided by summation over n RH of tau n. Okay, so and similarly you would compute the average of mean squared value, and then you would also compute the RMS delay spread. Okay, so basically we have characterized the time variation, the dispersiveness of the channel in the two forms, which then leads us to the complete characterization of the channel. The time variation using the Bessel expressions relating to the power spectrum. The power delay profile, if I take the Fourier transform, gives me a correlation function which tells me how the correlation of the frequency response changes. So that then tells me how to compute something called the coherence bandwidth. So the important two parameters that we need in our discussion are coherence time 9 by 16 pi fd, the coherence bandwidth 1 by 5 times sigma tau, and these are the key parameters which will characterize both the time variation, also the variation across the different frequencies. This is useful for us to look at this figure because the channel response is given by the red line, but depending upon the bandwidth of your signal, the channel response may look flat or it may look that it is changing, so frequency selective. So basically that then leads us to a classification of channels based on the symbol duration compared to coherence time. If your symbol duration is much less than coherence time, we call it as a slow fading channel. If it does not satisfy that, then it becomes fast fading. Now, if the signal bandwidth is much less than the coherence bandwidth, the frequency range over which the frequency response is correlated, then it becomes a frequency flat fading channel. Frequency flat means the frequency response is flat, the impulse response is a delta function, so therefore there is no intersymbol interference. So that's a desirable element to have. But on the other hand, if you have frequency selective fading, then you would have to have some form of equalization, which led us to the following terminology, that channels may be flat or selective in time, that means not changing or changing. In terms of the frequency response over the bandwidth of the channel, it could be flat, that means no ASI, or if it has frequency variation, then you would need an equalizer for those particular types of channels. Okay. So that more or less gave us a characterization of the Whiteson stationary uncorrelated scattering model and helped us to understand The next few lectures, basically lectures 29 to 31, had to do with our ability to generate Rayleigh fading on a computer. So that was lectures 29 to 31. So we had the following three models: the Clark and Gans, Smith model. Smith model, this figure you will remember, basically you did it completely in the frequency domain, and of course the time domain approach, which was the Jakes model. So the Smith model basically had to deal with the size of the FFT. That was an important element that would come out, and the size of the FFT depended on two parameters. One was delta F, the frequency resolution that you wanted for the Doppler spectra. The other one was controlled, was not in our control. It was basically the sampling frequency of the signal that you were trying to generate. So this is the sampling frequency. Okay, so the size of the FFT, so if you were to think of this all the way up to Fs by 2 and on this side to minus Fs by 2, the size of the FFT, NFFT is equal to Fs divided by delta F. And this number could be very large depending upon how much resolution you want to achieve for your in terms of the representation of the Doppler spectrum. On the other hand, the Jakes model gave us a very compact yet very accurate way of working with the signals. So we wrote down expression for ZR of t, Zi of t, obtained what should be the scale factors to get unit variance. So variance of 1/2 actually, scale 1 and scale 2, and then verified all of the properties of the the Jakes model. If you have to give in the Doppler frequency, what is the sampling or the spacing between the fading waveform that you want, what is the number of samples that you want, and then it will generate with the guarantee that the real and imaginary part are uncorrelated. Each of them has got a variance of 1/2. The expected value of ZR of n is equal to Zi of n is equal to 0. They are 0 mean, and they have the desired correlation in terms of the Bessel function. Okay, and this we verified through the trapezoidal approximation, and so basically this is what helps us generate these waveforms on a computer. Okay. Last few lectures we entered the domain of diversity by looking at the benefits of diversity. We showed that maybe we'll just summarize before we get to this graph, the different forms. Selection diversity was the simplest form that we had discussed. This was basically choosing the best of the antennas that are available to us of gamma m. We showed that even selection diversity gave us a change of slope, and therefore our understanding is that diversity is going to change the statistics of the fading and help us achieve closer to the performance of a AWGN channel. And the statistics of a fading channel. So what is the probability that you are in a fade when you have selection diversity? This is the same as the probability that all your antennas are below the threshold for fade. This we showed is 1 minus gamma e power minus gamma th. e power minus gamma th by gamma raised to the power m. Okay? And this is approximately gamma threshold divided with gamma raised to the power m. In the context of selection diversity, we also made reference to weak antennas as opposed to strong antennas, and when do weak antennas, when are they helpful, when are they of not much use, and what are the benefits and trade-offs. We had discussed that. Better than selection diversity was diversity combining, where we saw that we could get the benefit of both channels, and this then led us to the optimal combining, which was maximal ratio combining, MRC. And maximal ratio combining required us to use the gain coefficients to be zk star divided by sigma n comma k whole squared. So basically it was co-phasing plus a weighting based on the noise variance of that particular channel. Okay. For the both for selection diversity and for maximal ratio combining, we obtained the statistics, and then basically we were able to show the performance of BER performance with diversity. And let me just write down one last result. Basically, we also showed the following, that gamma MRC is better than or equal to gamma equal gain combining, which is better than gamma selection combining, and this one achieves the sum, instantaneously achieves the sum of the different SNRs. This one achieves something slightly less, 1 over m summation root gamma k whole squared, and this one basically selects the best of all the antennas, gamma 1 to gamma m. And we also showed that on when you take the average value, this achieves m times gamma, this achieves gamma times 1 plus m minus 1 pi by 4, and this one achieves a diminishing return 1 plus 1 by 2 all the way to 1 over m. Okay, and in the interest of time, let me just summarize the last statement, that we showed that when you take the MRC expression, you can split it into array gain and diversity gain, and recognizing that the received diversity techniques give you a combination of both benefits. On the other hand, if you are limited to TX diversity, then you will give up the array gain, but you will still get diversity gain, but you will need the knowledge of the signal channel at the transmitter. The only exception is the Alamuti scheme. It is a transmit diversity scheme without CSIT, which achieves the diversity gain of a 2-branch system. Diversity gain, of course, it being a transmit diversity scheme, it does not achieve the array gain. Okay, so that pretty much was the span of what we had covered all the way up to lecture 36 in the context of diversity. Okay, hopefully that sort of helps in sort of putting the pieces together. We will look at assignment 4, and any doubts to be cleared on assignment 4, please come to ESB 242 between 5 and 6 p.m. Thank you.